It's a great pleasure to introduce our last speaker, Bob MacPherson from IAS. He'll be talking about torus, spaces of torus action.
Thank you very much. I only had one mathematical conversation with Jim Simons. As it turned out, it was just at the cusp, at the very last minute, that he was doing mathematics and when he was starting off on financial things. But I didn't know that. Anyhow, we talked about Pontryagin classes of polyhedra and polylogarithms and other things. It was, as other people have described, an extremely inspiring talk, and as you may know, I went on to think about these things for many years after that. One thing I remember about this is that every so often in the conversation he'd stop. We were talking at the ITS in France, and every so often in the conversation he'd stop and say, "The French franc is going to fall." Then he really involved in this, and then I did a really stupid thing. I went home and thought, you know, he's just a math type like me. He doesn't know anything. Of course, I had gotten advice from what turns out to be one of the financial experts of our time, and now people pay quite a bit for this sort of advice. I was trying to remember the date so I could establish that.
Yeah, will it fall?
Well, I'm going to talk about joint work with Mark Goreski and Bob Kotwitz. This is, you can, the paper has now appeared in Invenciones, and you can read it. It's a very abstract paper that talks about causal duality and equivariant derived categories and so on. But I'm going to abstract from it the sort of ordinary homology consequences. Actually, we didn't set about to think about topology of torus actions at all. We set about to solve a problem in number theory, which is there's an intriguing open conjecture which I can advertise, which is Langland's fundamental lemma, so-called. Conjecture. Which is basically a conjecture about certain algebraic varieties. I mean, the conjecture is originally about finite sets, but anyhow, you have a couple of groups related by a map on their L groups. They're dual groups, and then the conjecture says that certain Springer, affine Springer spaces here and should have cohomology related to certain affine Springer spaces for that one. Of course, the problem is that nobody knows how to get any geometric information about a group from geometric information about the dual group. So it's sort of hard to reduce this to topology. And the formula that I'm going to use, we use to give a proof of this in what's called the unramified equal valuation case, which is in some sense the acentral case. This conjecture, well, it's sort of anyhow. Nowadays, people like Arthur and Clauzel are proving theorems, assuming that you knew this conjecture. So it's a sort of like certain other conjectures in mathematics. There's a whole theory being based on the idea that it's probably true and will probably be proved someday. Well, anyhow, but what I'm going to talk about is strictly topology, not number theory. So suppose you have a space with a torus action. So, for example, it might be the space might be an ordinary 2 torus, and the group might be a circle group, sort of spinning everything around in orbits like this. Let's see. These colors are not so. All right. Then that induces a number of structures on the space which are well known. So I'm going to just sort of talk about well-known material for a while. First of all, it induces a structure on the ordinary homology of the space. So recall that the homology of the space is I cycles in X modulo the boundaries of I plus 1 chains. So an I cycle might be something like this, and these two cycles would be equivalent because their difference is an I plus 1 chain like that. You know, in the early days of homology, there was a big dispute about this word in. People were discussing whether the cycles should lie in X or be mapped into X, and there were these two theories, and then they finally decided they were the same. So, for example, if I have a 1 cycle mapping to a point, that is homologous to 0 because that's the boundary of a 2 chain like that. So this is, I mean, anyhow, it's interesting to go back and see how confused they were at one time on this issue. Well, what does the circle action do? The circle, the first thing the circle action does is give us some operations. So the sweep, I can sweep if I take a cycle like a point and just sort of sweep it around a circle, then I get a cycle like this. And so I have a sweep operation that raises the degree by 1. Or I could sweep a chain like this and get the whole torus. You can easily check that if I had two circle actions, a 2 torus action, then I have a sweep action for each one, and the two and the anti-commute. So basically, I get an operation of an exterior algebra, and this is a sort of well known. The homology of the space becomes a module over the ring, the homology of the group, which is a ring by the Pontryagin product, and the homology of the torus is an exterior algebra. Okay, well, in the event that suppose I have a chain and the sweep of this chain is equal to 0, is equal to 0 in homology. That means the sweep of this chain is the boundary of something, and that means I can take the thing it's the boundary of, that now something with boundary, but then I can sweep that. And now this gives me a new cycle. You can calculate that it is a cycle, essentially because the sweep commutes with the boundary. A good example to think of is the 3-sphere. Suppose I take a point in the 3-sphere with the usual hopped torus action. Then if I sweep the point, I get so this original point is C, and if I sweep it, I get a circle like this, and that's, of course, the boundary of something. It's the boundary of a disk. So this is the boundary inverse of the sweep of C. And then if I sweep that, I fill out the whole 3-sphere. So so I get a non-zero homology class. And so on. There's a whole bunch of, this is a sort of a secondary operation which is defined only if this is equal to 0, but if I choose a different choice here, I won't quite get the same answer, but there'll be an indeterminacy. It's the usual homology operation situation. And then if the secondary homology operation is 0, there's a tertiary one, sweep, boundary inverse sweep, and so on. So there are all these operations which raise degrees by various amounts. Just to give the flavor of the general picture, if I have a larger torus acting, there's something else I can do, which is I can sweep by the first one. I mean, suppose that both sweeps are 0. I can do something like that. And once you've seen that, then you've sort of seen the general picture from, I mean, you can figure out what are all the various homology operations that you can do on the space. Okay. Well, this is usually summarized by saying that there's a spectral sequence, and these are the differentials of the spectral sequence. But anyhow, the spaces that I'm going to be concerned about are spaces such that all of these operations give 0. So we say that X is equivariantly formal if all of these operations are 0. There's no way I can generate new cycles from old cycles by any such procedure by using the group action. So this is in some sense saying that the group doesn't move points around too much in some homological sense. Nevertheless, there are lots of examples of these spaces. So for example, if X is any Kähler manifold and the circle action is the restriction of a holomorphic C star to the N action, then it will be equivariantly formal for Hodge reasons. In fact, what you really need is that the homology should be pure, i.e. its Deligne weight is related to its degree in the same way as it is for non-singular spaces. I should say the examples that I'm personally most interested in are singular, but nevertheless, for example, the one that comes up here, but nevertheless they are pure. There are a lot of such singular pure spaces like Schubert varieties and Springer fibers and well, okay. Pure means that the Deligne, if the space is an algebraic variety and therefore the cohomology has a Deligne weight, it means that the Deligne weight is the same as the, well, what is it, Spencer, twice the degree. Okay, just the degree, yeah, right, sorry, I always forget the normalization, right. Okay, so there are a lot of spaces like that. Well, anyone who knows about homology and group actions knows that it isn't the ordinary homology that people usually compute these days. It's the equivariant homology. So I also want to give a little well, just for fun, I want to give a definition of equivariant homology. Well, there are two standard definitions. There's a sort of homotopy theoretic one, and there's the one which I'm sure most people here like, which sort of uses differential forms. But I want to give a third one, which is sort of well adopted to these spaces and to drawing pictures, which I like to do. So the equivariant homology is equal to now mapped in I plus, let's say that G is an n torus. I plus n chains, cycles, with a free G action modulo the boundaries of the same with I plus 1. So mapped in I plus n plus 1 chains, again with a free G action. And the important word there is free. No, this is just abstract nonsense. So, for example, with the example we had there, there's a zero chain, which is so that's an element of H 0 G of X. So you see it has a free action, and it's a chain whose physical dimension is one more than the thing you use to intersect it, and then the whole thing is an element of H 2 G of X. An interesting case in point is a point. So suppose you have a point, then you start having interesting classes. So you can suppose the torus again is a circle. Well, you have a circle with a free action, just a circle of a copy of itself, and a map in. Now, remember, as I said before, that did something in ordinary homology, so we didn't have to really consider it. But in equivariant homology, it doesn't bound anything anymore, because if I tried to fill it in with this disk, any way I extend this action, I'd have at least a fixed point there somewhere in the middle. And you can try to imagine other ways, something like this, but then you can't imagine how to extend the circle action. Anyhow, there's no way to do it. Yes, thank you. So 1. And similarly, if I take the 3-sphere with the hop action I was just talking about, that gives me another such thing. Now, so I have all odd dimensional spheres, and then if the torus were of dimension greater than 1, I could start taking products of these spheres, one of these spheres for each of the factors in the torus, and it turns out that all of those classes together generate the homology of the point. Well, what the answer is, let's see. so we're in the usual situation here where for drawing pictures, homology is most convenient, but for writing formulas, cohomology is most convenient. So at least as a group, the cohomology of X, I'm always using rational coefficients, is the dual space to the homology of X. And the same as the equivariant homology, cohomology. Is just the dual space, but the cohomology has a ring structure, and that's why it's more convenient. So the result is that the equivariant cohomology of a point is equal to a polynomial ring. Polynomial functions on the Lie algebra of G. So just polynomials and n variables, but if you think about its functoriality, it turns out to be polynomial functions on the oh my god. Do I have the duality wrong? No, I think it's right. Yeah, I think. It's another generator. It's a thing which is sort of dual to the function x over there. This generator, this circle, is dual to the function 1 over there, and the S3 is dual to the function x, and S5 is dual to the function x squared, and so on. So this is a way of picturing the dual basis to the basis of monomials over there in the in that description. Okay, let me draw just one more picture of a non-trivial relation. Well, in fact, perhaps I should make two comments about the yeah. What?
You have in mind that you use torus.
Yes. Right. Yeah. I mean, otherwise I would be taking biogroup invariance or something like that, and it's essentially, but there's essentially no more topological information when you consider a compact Lie group. Well, another example is the sphere, where the circle acts by the 24-hour day, rotating with. Guess we just had a 23-hour day. Anyhow, so there are two comments to make about this. First of all, there's an equivariant cycle which, sends the circle to any line of any orbit of the group. But this cycle can be sort of moved to a cycle which just to a mapped-in cycle which just hits the pole, because you see there's an obvious equivariant homology where I take this cycle crossed with an interval and then map it in, and then this whole bottom circle gets mapped into this pole, and so that's a homology that's in the denominator of this fraction here, and it shows that the cycle can be moved to just hit one of the poles or hit the other of the two poles. And furthermore, a similar picture with a cylinder going all the way up and down shows that, well, that if I map this is just cylindrical coordinates, that if I map a circle in at the bottom, it's the same as mapping the circle in at the top. So this is a relation. Well, these two pictures are typical. What I want to say is that for a large class of spaces, all cycles look like this one. That is, all cycles are sort of mapped into the fixed points. And all relations between the cycles are like this one. That is, all relations between the cycles come from two spheres which connect these fixed points. So to state a theorem, I'm going to be more restrictive than is necessary, but you get a nice theorem this way. So I want to further restrict the class of spaces. If I have any with a circle action, I can consider it one skeleton. And this is the union of the zero and one-dimensional orbits. So I'm mainly interested in the case where the torus is larger than one-dimensional, or else this would be everything. And so that's a possibly small piece of the space X. And my hypothesis is that the one skeleton looks like a balloon sculpture. Okay, so let me draw a balloon sculpture. But you've all seen them if you've been to a fair or to Disney World or something like that. Well, it don't have much space. All right. Okay, so what are the essential ingredients here? The fixed points then here is a finite set. So and so on. And then the one-dimensional orbits form these balloons. Each one-dimensional orbit comes in a two-sphere with the standard rotation like that one, rotating the two-sphere around. So it has two fixed points, and
how about the two spheres? Well, the one sphere there are points and circles.
This is abuse of language. But on the other hand, I'm abusing language already talking about that as an I-cycle. I mean, dimensions are a little bit funny here. But I think, see, in some sense, in the equivariant sense, I think this is the appropriate analog of a one skeleton. I mean, the theorem I'm going to state says that from this data here, you can calculate the cohomology of the space, and I think of it as philosophically analogous to the sort of Witten-style presentation of Morse theory, where if you have a Morse function from the critical points plus the one-dimensional orbits connecting them of adjacent dimension, you can calculate the entire cohomology of the space. So the same is true here. It's a kind of an equivariant one skeleton. All right. Yeah, perhaps the more appropriate thing to say, which will come up later, is that this whole thing can be summarized by a graph. If I divide by the circle action, then I get something which is properly one-dimensional. Well, so now the theorem, the simplest version, is suppose that well, I mean, if the group is too small, well, I mean, well, for example, a one-dimensional group acting on anything that other than a bunch of balloons itself. So I guess a one-dimensional circle acting on CP2 would be perhaps the simplest example. Right. So suppose that first of all, X is equivariantly formal. And second, that the one skeleton of X is a balloon sculpture. Okay, so I'm going to assume both these hypotheses. These hypotheses, of course, work contrary to each other. Equivariantly formal says the group doesn't move things around very much, and X1 being a balloon sculpture says the group moves things around enough that it doesn't have too many small orbits. And so perhaps it's not too surprising that with these hypotheses working against each other, you get a good description of the cohomology. So then the equivariant cohomology of X is the subring of the direct sum over the fixed points of the polynomials on the Lie algebra of T, the polynomial functions on the Lie algebra of T. Okay, so that was the equivariant cohomology of the thing itself, cut out by. So I said subring, and I have to tell you which subring. By the equations. Okay, so what does an element of this direct sum look like? Well, it looks like a sequence of polynomials, one for each fixed point. For each, so I'm going to have a relation for each bi for each balloon. Then let me call it this way: F Ni restricted to the Lie algebra of the stabilizer of B I is equal to F Si, sorry, these should be small f's. They're supposed to be polynomial functions, not fixed point sets, restricted to the Lie algebra of the stabilizer of BI. Okay, so what do I mean? A BI looks like this. It has two fixed points. I just choose them in arbitrary order and call this Ni and this Si for North Pole and South Pole. So each BI gives me three pieces of data. In the first place, because all these one-dimensional orbits are sort of lined up that way, it means that their Lie algebra of the stabilizer is all going to be the same. So the first piece of data is that I only one dimension of the group is doing anything, so n minus one dimensions of the group must be doing nothing, and that's the stabilizer. Then the other piece of data, the other two pieces of data are the 2 points that it connects. So I use these three pieces of data to say that the function on one of them, restricted to this Lie algebra of the stabilizer, is equal to the function on the other, restricted to the same Lie algebra of the stabilizer. Okay, so that's a complete answer, and then also you get a complete answer for the again. The function in that direct sum, the polynomial function in that direct sum, corresponding to the point Ni on this balloon. So I'm symbolizing an element in that direct sum as something like F1, F2, F3, and so on. Then furthermore, the ordinary homology of X is equal to this is, in this context, is sort of well known, is equal to the equivariant cohomology of X divided by the ideal generated by things F times, where F of 0 is equal to 0. Okay, so I have the maximal ideal in the polynomial ring of things which vanished at the origin, and this maximal ideal then produces an ideal in this ring, because this ring is a module over that. I just multiply each of the f's by the same polynomial, and then I divide out by that ideal, and I get the ordinary cohomology. So as advertised, the whole cohomology picture is given away by this combinatorial set of data like that. Let's see. These relations. So I already said that how to think of this is that the polynomial functions on the Lie algebra of T, that's the equivariant cohomology of the fixed point set itself. Now this subspace, cutting out a subspace in cohomology, well, that's dual to taking a quotient space in homology. The quotient space in homology is exactly the one given by this picture. So here's a fundamental relation that says that this circle is homologous to that circle in equivariant homology. So that's essentially the only picture. I mean, there's a similar picture if I had a three-sphere or something. So basically, it's saying that the only relations are this relation sort of souped up with the appropriate algebra. So somehow what this theorem is saying is that the homology is sort of generated by the homology of the fixed points, and all the relations can be pushed. I mean, wherever these relations go in the space, they can all be pushed down into the one skeleton. One would conjecture that these are the first two statements of a whole infinite tower of statements, but I don't know how to prove it. I mean, if you have a relation among the relations, suppose you have two different ways of showing that something is homologous, perhaps directly this way and also looping around that way, then those relations, I mean, it should be a homology between those relations, which is in the two skeleton and so on. So I just don't know the answer. It's true for the first two numbers. I don't know if it's true for the rest. But anyhow, this is enough to calculate the cohomology. So let me do two things. First of all, I'd like to talk about this data because this data is data that I love. So you can summarize this data. Okay, the data that I'm talking about is for each balloon, it connects two fixed points. So identifying those two fixed points, and it also gives me an angle in the space. It gives me a hyperplane, the Lie algebra, the state. Well, this data naturally is going to be simpler then if I go back to the Lie algebra, to the dual of the Lie algebra. So I get a picture in the dual of the Lie algebra, which is an angle of a line. Then I can try to summarize the data taking an embedded graph. I can take an embedded graph where the vertices of the graph correspond to the fixed points. And I have an edge between every pair of fixed points if and then the angle of that edge is the perpendicular in the Lie algebra dual of this stabilizer here. Well, how do I know I can make such a graph that I don't get a contradiction, that I don't go around a loop with all these edges and end up not being able to close? Well, that's because of the... I mean, it turns out that for at least the Kähler case, which is the case that we're interested in, or perhaps singular algebraic varieties as well, that you do it just by taking the moment map image of the one skeleton. So this graph is actually the moment map image of the one skeleton. Well, as you may know, these moment maps are glorious things, and what this is saying is that from this data, the vertices, these vertices and edges, you can actually calculate the cohomology of the space by this algebraic construction, which is a lot of fun. So I brought along my model here. This is the flag manifold of flags in C4 and complete flags in C4, and I have a 3 torus acting on complete flags in C4. Well, a 4 torus actually, but one of the circles does nothing, just the diagonal matrices. And this produces a very well-known and highly studied moment map image, which is a permutahedron like this. It's sort of known for all of the groups, but also known as the one-dimensional orbits. The various lines here, for example, these large plastic things are the fixed points, and the lines, either plastic or string, are the one-dimensional orbits, and they all neatly line up like that. So really, the point of this, I guess, is that, I mean, I've loved actually playing with polyhedral models like this since high school, and so now I have an excuse to do it and say that I'm calculating equivariant cohomology groups.
Angle of the line, what do you mean exactly?
So the line is some some angle in space. If I translated it to the origin, it would be a one-dimensional subspace of direction. Yeah, right, direction. It would be a one-dimensional subspace of the dual of the Lie algebra, and that corresponds to a hyperplane in the Lie algebra itself. And so it's that hyperplane that I use there. Okay, well, let me just finish by giving a sample calculation so you can see the kind of fun you get to have with this. This is the most by the way, it's an interesting puzzle. Somehow, how is it that you can calculate the whole cohomology, the whole space, by looking at such a thin subset of the space? You know, what's the rest of the space doing there? Of course, the answer is the rest of the space is just making the thing equivariantly formal. It's not contributing to the calculation at all. Okay, well, suppose I took CP2, the most easy example of all, and I have this is given by homogeneous coordinates, Z1, Z0, Z1, Z2, not all 0, and this, if I multiply them all by the same number, I get the same result. And then I have a 2 torus acting on this, say lambda mu, if these are both unit complex numbers, times Z0, Z1, Z2 is equal to Z0 lambda Z1 mu Z2. Okay, so it's easy to see that that this satisfies all the hypotheses. This is a restriction of a C star action, and it's the fixed points are just the 3 points 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And then, so for each of these, I give myself a polynomial function on the Lie algebra. So the Lie algebra is two-dimensional. I draw that two-dimensional space like this. So, this, now in my picture, this direct sum there is, I'm imagining a polynomial function here, a polynomial function here, and a polynomial function here, and then the union of those three is the thing. Then I want to cut out some relations in there. Well, there are three lines. Namely the three balloons, namely Z0, Z1, 0, and so on. Z0, 0, Z2, 0, Z1, Z2. So now I have two choices. Well, I mean, perhaps let me do it this way. Normalize somehow the moment map. Well, okay. So let's look at this one first. This line, what is the stabilizer? Well, the stabilizer is the things of the form lambda lambda. The stabilizer is the diagonal, because if I multiply all these numbers by a lambda, it corresponds to the same point. And so what does that mean? I take the two fixed points in its closure, which are these two. And it says that if I restrict the polynomial function here to this line, I get the same as the restriction of the polynomial function here to this line. Okay. This one, I guess the stabilizer is the second coordinate. And its two fixed points are these two. So if I take this function, restrict it to this line, I get this function restricted to that line. And this one, similarly, is the stabilizer is the first coordinate. And did I? Okay. So this now is a sort of a graphic picture of the restrictions that I have to put on the polynomial functions. That is, these two polynomial functions restricted to this green line have to be equal. Well, when you build a ring by taking functions on affine spaces and making restrictions of equality like this, that actually has a neat interpretation in terms of spec of the ring. That is, I can build the space that this is polynomial functions on, that is spec of the equivariant homology, just by performing these gluings. So what I want to do is I want to take these three planes and glue them along those lines. You know, you give this, like it comes on a cereal box, and you give it to the kids. Glue this green line to this green line, and so on. And so then the question is, what do you get? Well, you can probably visualize it, but what you get is the union of the three coordinate planes. Whoops. Where the three colored lines are the axes. So this is the remnant of the red line, and the remnant of the green line is coming here with two planes glued together. The orange line isn't very... Wait, it's wrong color. No, it's not. Right. So polynomial functions on that then is the equivariant cohomology of the of CP2 with this torus action. Then finally, I get the ordinary cohomology by dividing out by this relation. If you think about this relation in terms of this is like restricting the intersecting this variety with the triple diagonal, the thing where the three coordinates are equal. So now if you take polynomial functions on this configuration and restrict it to the thing where all three coordinates are equal, you get polynomial functions on that line with a sort of a threefold thickening at 0. It's just sort of intersection theory. And so you end up with C of x divided by what, x cubed. Well, so that's the answer that our that we teach in our freshman calculus courses, but done by a different way. Okay, thank you.
It seems like this equivariant formality is very central in this whole discussion. Is there any hope of relaxing that? Is there a conjectural statement of what should replace it?
The question is there any similar computation with equivariant formality relaxed? And the answer is I don't know of any. Our motivating examples from number theory had equivariant formality, so we were happy with the hypothesis. But yeah, it's an interesting question.
What is the equivariant formality equivalent to saying that the equivariant homology just splits up as the ordinary homology tensor polynomials, or just one?
Yeah, in an appropriate right. There's a spectral sequence from that too. Right, exactly. Yeah.
So what happens when you take the balloons to have different stabilizers? Can you say anything about the identifications of the image with those things?
I didn't understand.
So balloons are just spheres with a certain action.
Yes.
You have different actions on the sphere, on those balloons.
I don't think you can do it. You can't fit it together. Because stabilizers, tend to, well, there are only discretely many stabilizers, but there's a continuous line, so they can't sort of jump as you go down.
So you cannot say anything about the meaning in that case.
How strict is your choice of these balloons? Are they really like the balloons Franz made out of the cylinders, where there's a definite north-south, north-south, north-south?
No, the north-south didn't matter. It was just...
You could just take a bunch of spheres and just join them at north and south poles to each other randomly.
Yeah. If I switch south and north, the formula doesn't change. It was just that I couldn't figure out how to write it down without calling one north and one south.
Before we thank Bob again, I want to say that Blaine is going to have a few words to say. Thank you again.